All right, wonderful. So take it away, Riccardo.
Yes. Okay, thank you very much for inviting me at this weird hour. So the subject it's here. Okay, let me start. Oops, it's already not moving. Okay, so yeah, if I don't, sorry, 1 second. Okay, if I don't put the thing here, it doesn't. Okay, well, I don't know. Sorry, guys. Sometimes it gets stuck. Okay, so this is work I did with my collaborators, in particular Alexander Monin and my two students, Gilles Badel and Gabriel Cuomo, in two papers that came out last year. Another paper, it's in progress, dealing with extra computations, in particular 3-point functions. This is going to be probably in the next few, I don't know, in the summer. There have been other groups doing related work, closely related work, or vaguely related work. And they all came up last summer. It's a paper by Grassi, Komargotsky, and Tizzano in the supersymmetric context, and a paper by Arias Tamargo, Rodriguez Gomez, and Russo, which is overlapping a little bit with what more significantly what we are doing. Only I think they are doing just a particular case of what we do. And then there's a similar paper, again, doing part of what we do by Masataka Watanabe. Let me get to the main point. Okay, so when we deal with physical systems, we are familiar with normally familiar with two main dichotomies: weak versus strong coupling, and classical versus quantum. And these two pairs of extremes are quickly and nicely illustrated by considering the path integral description of your system. Okay, in particular, the case where we have weak coupling corresponds to the case where the path integral can be reliably computed as a convergent loop expansion around some leading trajectory, gamma classical. Okay, okay. So you have a leading trajectory, and then you compute your amplitude, your observables. You organize your computation in terms of small fluctuations around this trajectory. Now, in this situation, you can further distinguish between classical or semi-classical and quantum observables. Very schematically, any quantity or any observable, you can compute it, and it will consist of two parts. It will consist of a contribution that comes from the value of the variables on the trajectories and the contribution from the fluctuations. And now it's pretty obvious how to describe classical versus quantum. If you have an observable for which the contribution from the trajectory dominates the result, okay, you could call this a semi-classical variable. And an example of this is, well, everything before quantum mechanics, everyday life. And on the other hand, in the situation where the quantum corrections are comparable or even bigger than the classical contribution, you could say that this is a quantum observable. Just a simple example, just consider weakly coupled field theory and consider the 4-point function, okay, for fields. That's a genuine quantum effect. It just captures quantum fluctuations around the trivial trajectory phi equals 0. Okay. And then the other possibility is to have strong coupling. If you have strong coupling, it just means that your path integral can in no way be approximated by the contribution around a certain trajectory. Okay, it's all spread out. Okay, it's not localized in the space of variables. And in this respect, it doesn't make sense. I mean, everything is quantum, all observables. You cannot even talk about the classical limit of an observable. And of course, these are limiting situations. I can imagine theories where in some regime it's strongly coupled and in others it's weakly coupled. Take QCD, okay, around 1 GeV, everything is strongly coupled. But if you go to long distances, you have a weakly coupled pion description. So anyway, that's that's just a general characterization. Now, in particle physics and in phenomenology and the common practice, also because it happens at the standard model, through a broad range of phenomena is weakly coupled. We are familiar with the computations of processes with few legs, weakly coupled quantum field theory. Okay, so 222, 223, and this corresponds to small quantum fluctuations around the trivial trajectory, the vacuum phi equals 0. And this is nice. Okay, it's nice if you want from the point of view of science as a whole, because by studying this simple process, and this is the essence of particle physics, you study simple, really boring processes in order to zoom on the laws, on the Lagrangian. Our goal is to find what the Lagrangian is. Then what other can happen with this Lagrangian is, of course, interesting, but the primary goal of particle physics, in a sense, if you want to put it in a real nutshell, is to find out the Lagrangian. Okay, so that's the situation, and that's what we are mostly familiar with. On the other hand, and here we are getting more into the domain of phenomena more than laws, it's known that even when you have a weakly coupled theory, if you consider a number of legs that grows, if the number of legs is big enough, the ordinary perturbative expansion breaks down. Okay? And the question and the main goal of this talk is to ask, so how do we describe physics in this regime? So what I want to consider is the regime where I have a weakly coupled field theory, but I'm considering processes with a sufficient number of legs for perturbation theory not to apply. The question, how do we describe this scenario? How does it fit in the classification I presented in the previous transparency? Is it strongly coupled? The fact that there's no perturbation theory, what does it mean that we cannot do perturbation theory in this situation? Now, this, I suspect that this has been thought many times before, and certainly it has been thought by the particle physics communities, has been considered, this question has been considered by the particle physics community in the 90s, okay, in the beginning to mid 90s. And the prototypical question that was being asked at the time was, well, consider a very simple bosonic field theory, phi to the fourth, okay? And let's consider, and oh, by the way, the stuff I'm going to talk about now is nicely illustrated, if you want to get a very quick introduction to this, by a very old review by Rubakov from the mid-90s. Okay, so you just read that. That is all that I'm saying here in the next two transparencies. So consider, for instance, phi to the fourth, and consider injecting, coupling the field to some source, okay? And this source just produces a virtual quantum of this phi to the fourth theory, and this virtual quantum, which has more energy than its mass, will cascade and produce more quanta, okay? And in this scenario, you can compute, it turns out that you can compute if you stay close to threshold, namely, if the energy here is such that for a certain number n of final state particles, they're all pretty slow, they're close to threshold, the amplitude for the process 1 to n can be computed by a nice little trick, which was, I believe, first found by Lowell Brown, again, early 90s. All the papers, you find them in the review by Rubakov, so I'm not quoting anyone else. So, okay, you get this result, you get an n factorial coming from the number, from the various permutations that you can get, times this factor, which is just the number of vertices. Now, from this, you can compute the probability, or the cross-section is more like a probability, for 1 to go to n. Okay, just square it, divide, integrate in the phase space. The phase space, these are identical particles. When you square these, you get an n factorial squared, but you get a 1 over n factorial from the phase space. At the end of the day, you get an expression like this. There's an n factorial, there's a power of lambda, it corresponds to the number of vertices, the number of final, the minimal number of vertices that you need to produce n final state particles. It's n, okay, n over 2. And then you square it is this. And then there is the phase space, okay, the phase space is 0 if all these particles were exactly at rest. And if you're close to threshold, then you get the phase space scales with this power of epsilon, where epsilon is the kinetic energy per quantum. Okay, produce n particles, and their average kinetic energy for each of them is given by this parameter epsilon. So what do we do with this formula? Well, this formula, it certainly shows you that for moderate n and lambda small, this gives you certainly a suppressed probability. However, even though for small lambda, this is exponentially suppressed, okay, when n becomes large, and also suppressed in epsilon when n becomes large, the factorial in front grows faster than an exponential. Remember, the factorial in your Stirling formula goes like e to the n log n, okay? So it grows faster. So eventually this overcomes this suppression, and so you exceed probability 1, indicating that you're doing something that is not licit, okay? You're in a domain where you cannot do perturbation theory, okay? And as a matter of fact, if you compute the first corrections to this amplitude, okay, you find that this is the 3-level amplitude, you find that the corrections scale with a positive power of n times lambda. So if you keep lambda small, when n becomes large, eventually the loop expansion breaks down. So it seems like it's a mess to do this computation, okay? Yes, it is, but not completely, okay? In fact, and this was proven, I believe, first by Libanov, Rubakov, Son, and Troitsky in '94. I believe, I could be wrong, but this is what I remember being the first paper where this was done. So one can prove that all these large loop effects indeed resum, okay? You can resum them. I mean, you have larger and larger effect, but they're just powers of the same effect, and you can resum them into an exponential, okay? And the exponential for the probability has this form, okay? It's n times a function of lambda times n times this parameter epsilon, which is the energy per quantum. Now, these exponential forms, if you multiply this expression here by lambda and divide by lambda, it looks like a typical semiclassical expression, okay? It has, you can treat lambda n times a fixed parameter, and then you have an amplitude and an exponent that goes like 1 over lambda, typical of a semiclassical amplitude, okay? So these people showed that you could do this resummation, and the form of the result, they claim, suggests that there should be a non-trivial semiclassical trajectory described in the process, okay? And in fact, this semiclassical methodology and trajectory was proven to exist by Son, I think in the year before, the year after, 95, I mean, back in the 90s, okay? So technically, the problem, therefore, seems that the reason why you see this lack or breakdown of perturbation theory is simply that the original computation, the one that I showed here, for when n is large, okay, the original computation was done by the standard approach, namely studying fluctuations around the vacuum, and that led to an expansion that did not stand up, okay, that was divergent. On the other hand, as proven by Son, there exists another trajectory along which you can expand, and when you expand along the trajectory, everything seems under control, okay? I mean, perturbation theory can be controlled. Now, the problem is that finding this trajectory, finding this other solution is not easy. It's easy, you can do it for lambda n small, okay? And epsilon also small. But when lambda n becomes big, in fact, not really lambda n, but lambda over 16 pi squared times n, which is, if you want the loop expansion parameters, time the number of legs, when it becomes of order 1, then you get entangled in tricky numerics, and it's not, I mean, it's a mess. There you cannot compute, okay, and it's complicated. Now this is a quantitative question. However, it's also not just academic, okay? Because what could happen, I mean, what you would like to understand what is the fate of this expression when n becomes large. When n is small, this f is negative, so this thing is exponentially suppressed. But it may be, there's still the logical possibility that when n becomes large, this function asymptotes to 0 from below, and that asymptotically you have a probability that asymptotes to 1, okay? So that you have the process of production of many particles becomes unsuppressed. Again, this is not totally academic because this theory phi to the 4 that we are considering here is hidden inside the bowels of the standard model, the Higgs sector, as precisely bosons with this interaction, the Higgs and the Eaton-Goldstone bosons. So this may be relevant for processes involving, at high energy, involving the production of many W and Higgses. And in fact, the regime where the corresponding coupling lambda n in the standard model becomes of order 1 is the regime where the number of final particles is the inverse of the loop factor of the standard model, which is between 100 and 1,000. So that given the mass of the Higgs and the W and the Z, this corresponds to energies that range between the 10 TeV and 100 TeV, which is the range of energies which we'll hopefully explore, I mean, a few decades from now, the next generation of energy colliders. It's also because of that that this argument experienced a revival of popularity in recent years, in particular in the work of Kose and collaborators, okay, who have made some claims, okay, about what happens in this regime. This is the subject that goes under the broad name of explosion. I personally don't think their claims are warranted, okay, but I must admit that I have not myself, and neither have they, okay, solved the tricky numerical problem that underlies this question, okay? So anyway, luckily or unluckily, there are still a few decades before this issue becomes very hot. And before that, my collaborators and I have thought, why not to strengthen our muscles with a simpler problem, in a problem where we can indeed find the semiclassical solution and really study in detail its properties, okay? And this is the subject I'm going to talk about today. I hope sometimes in the future to get back to this, but today I will focus on something else. So what
Riccardo,
we did—
could I ask a question?
Yes.
Ricardo, could I ask a question?
Yes.
I mean, I think everything you've talked about so far is in the threshold approximation, where you ignore the momentum of the final state particles. Why do we care about this? Isn't this just a really tiny part of the whole phase space?
I agree. It would be nice to have a computation for epsilon small, but not 0. In fact, this computation done by Kose et al. Is done, strictly speaking, I mean, they found the solution at lambda n finite, but at epsilon 0, and then they extrapolated the non-zero epsilon. Okay, so if there is a corner where I can do the computation, why not doing it? Of course, there are situations where lambda n is smaller and epsilon is bigger. I agree with you, but it would also be interesting to compute this one, right?
I mean, is there knowledge of how fast it rolls off with epsilon?
No.
I mean, basically the n factorial is because there's bosons in the final state, in the same state. So that's lasing. But as the bosons become non-identical because they have momentum, you should lose the n factorial.
I agree with you. Look, okay, let me state it in a different way. It would be nice to have this worked out cleanly to avoid confusion.
Okay.
I have little doubt that the result is what we all expect. I don't know whether this is sufficient to move forward. I have no doubt that the result is going to be, I have little doubt it's going to be suppressed, and that this effect, I agree, it has to do with the coherent effect at threshold. And but it would be nice to put it firmly on quantitative grounds, and this was not done.
So actually, can I make a very, very brief comment here just because it came up? I mean, one thing we noticed recently is that the cosmological case where gradients naturally dilute is a place where this easy case of essentially threshold is physically interesting and relevant. And so in that context, actually this factorial does exist. Yeah, so it's ironic, but it's because of inflationary expansion, de Sitter expansion, that the gradients become unimportant, and this regime is in fact physically interesting. But that doesn't answer the question on the bottom of your slide. It's just an orthogonal point.
I mean, yeah. I mean, if I can get control of various corners of parameter space, then I can. I mean, it's always better to be able to compute something rather than nothing.
Yeah, I certainly agree with that. Okay,
so now in thinking about a situation where you can go through a more complete computation, we thought about systems that are not totally uninteresting as well, right? So we thought about situations where control in the calculability is gained by two additional facts. One is that the large number of legs is associated to a conserved charge. And second, you have conformal symmetry, okay? So with these two additional symmetry ingredients is what will allow us to get through an example where we can go through the computation essentially till the end, or maybe get interesting quantitative results. And this is not completely uninteresting because systems like this have relevance beside quantum field theory per se, for instance, in condensed matter systems, right? Like the critical point of helium in 3 dimensions for liquidity. So what I want to consider is, so now I will shift in a sense to a different question, where again, the ingredients are the same. There's a coupling, there's a weakly coupled quantum field theory, and rather than studying correlators with small number of legs, we study correlator with large number of legs. And we enforce the existence of a large number of legs by studying objects with big charge, okay? So let me consider, therefore, the simplest situation where I can think of a charge, which is a theory with a U1 symmetry, a theory of a U1 charge boson phi, okay? So charge phi to the 4th, okay? In this situation, okay, again, you can consider the standard small number of legs computation, let's say the 2 to 2 scattering. You start with, what you do here, you do quantum fluctuations around the trivial solution and the computation of physical quantity like the 2 to 2 scattering organized as a loop series around the trivial solution. So you have 3 levels, 1 loop, 2 loops, and so forth. Let me consider in the same scenario the computation of physical properties of multi-leg operators. And I will be focusing for the whole, I mean, basically for the rest of this talk, to the simplest possible thing that I can attribute to an operator with a number of legs, which is its anomalous dimension. Let me take the operator phi to the n, okay, and let me consider the regime where n is much, much bigger than 1, okay. Let me indicate the insertion of this operator by this symbol, okay. This multi-leg thing I just indicated in what follows by this symbol. So now I want to consider the anomalous dimension, okay, and now here it is, okay, I can just at first order, at the leading order, 1 loop, I get a diagram of this type, okay, which contains 1 coupling, and I can pick, I can connect the n legs of the operator with the 2 legs of the interaction in this number of ways, okay, pick n. The first one picks n, the second one can only find n minus 1, okay. Can also go to 2 loops. 2 loops I get, among other things, I get objects like this one, where I pick 3 legs, okay, and therefore I get n, n minus 1, n minus 2, and lambda squared. Or I can also get things that have 2 loops, but only have 2 powers of n. Or I can go to things that have 3 loops and pick 4 legs and have even more powers, okay? So if I look at the diagrams here, I can, for instance, focus order by order in the loop expansion on the objects which have at each order in lambda the highest powers in n, very much like I do when I do the G, when I do the leading log. I can do the leading n series, okay? And the leading n series as form of this type, okay? There is an n overall, which is the natural unit of measure, okay? I started with an operator which is classical dimension n, so everything, there's an n that factors out. And once that is factored out, this series, the parameter that controls the expansion is lambda n. Very much like in the example I was discussing before in the case of multi-particle production. Okay? Precisely the same combination, lambda times n. And again, there are 16 powers of pi's as usual. And what you get is that just at face value, perturbation theory breaks down when this parameter lambda n over 16 pi squared is roughly bigger than 1.
So did you already resum the lambda n squared ones like you described before, or is that different in this case?
Excuse me?
Sorry, in the previous case, you had a resummation of the very leading contributions that were controlled by lambda times n squared, right?
Right. Yes, those ones were essentially resumming these ones. Because now it's like in the exponent, okay, you're just considering the 2-point function and this exponentiating the 2-point function. And then you also, so that would be these all powers. You see, you get that the 2-point function is e to the lambda n square log. Is that clear? In fact, let me perhaps answer your question this way. Actually, let me say it a different way. Here. So actually the situation when you consider loops is a little bit more involved. And let me just give you a very rough picture, okay? And let me just compute the loops, okay? And organize the loop series in terms of the powers of n, powers of lambda, and the logs that I expect to get. Okay, this is a 1-loop diagram. I have a log. This is a 2-loop diagram. You have a log square and a subleading log, and so on and so forth. And diagrams themselves, and then you, Eva, you will tell me at the end whether I'm partially answering your question or not, okay? So you can organize your diagrams in terms of connected diagrams, meaning that all the legs that come out of the operator are connected through interaction points, like here, or doubly connected or triply connected diagrams where the legs that come out are at their own lives. They are not connected by interaction points, okay? And clearly in this case, these cases are factorizations, okay, of the previous ones. Apart from the end behavior, they have the same loop squared, here cube, and so on and so forth. Now, it's clear that these terms that are multiply connected have many more power, at the same number of loops, have more powers of n, okay? Because you see, this is a 2-loop diagram, this is a 2-loop diagram, this has only n cubed because I'm picking 3 legs. Here I'm picking 4 legs, I get 4 powers of n. And here I get even more. Now, what one can check, and we did not, and I believe this can be proven, and we chose a different pathway. This can certainly be proven, I believe, by some general inductive argument on the structure of diagrams, is that the first half, the diagrams with the highest powers of n, in which are all multiply connected, actually exponentiate, okay? These guys here exponentiate, okay, in the wave function normalization, okay? I'm computing the anomalous dimension, okay? The anomalous dimension is simply the derivative of the logarithm of the wave function normalization of the operator. This is an operator with fixed charge, okay? It renormalizes multiplicatively, okay? And the anomalous dimension is simply the derivative of the log of z. And all these guys here exponentiate, okay? And namely, if I want to compute the anomalous dimension, it's only this guy that matters. And the same thing here, okay? So the anomalous dimension is generated, if you want, by the connected, very much like when you compute the vacuum, you compute the vacuum energy, you just look at the connected diagrams, okay? So only the connected diagrams contribute, okay? And therefore, the anomalous dimension starts with powers of this type, okay? You don't have powers like this.
Okay, thank you.
I don't know whether this addresses what you...
Yeah, I think it does, thank you.
Okay, so now, but by the way, this structure, we did not really, we were a bit lazy, we did not check it explicitly. We checked it up to 4 loops that it worked precisely like this. And then we thought of a different way to prove it to all orders, and I will present it in a moment. So all I'm saying is that the series can be, I will do it in a way that is non-diagrammatic. The series can be organized as a double expansion, okay? Very much like the RG, okay? The anomalous dimension divided by n, okay? As I said, the anomalous dimension is as an overall n, because there is already the n of the tree level, okay? So divided by n, and now what you get is organized as a double expansion, okay? You have an expansion in powers of lambda n, and so you have a polynomial, infinite polynomial in. So this is summing at, this is picking at every loop order the term with the highest powers of n. This is picking at every loop order the next term, okay, the term with subleading power of n, and so on and so forth. That's very similar to what you do when you do the RG. Okay, this will be picking when you do the RG resummation. The one loop RG picks in every diagram the contribution with the highest log power, and the next to leading RG, the 2-loop RG, picks the next to leading log, the one with 1 less power of log. And that's also similar, if you want, even though n here is the number of legs and not the number of color, to, there's also an analogy with the 't Hooft-Largen expansion, okay? Again, I can write this, just simply multiply and divide by n each term, and now absorb lambda n into a new P1 bar, and this can be written as a sum in inverse powers of n, okay? So now the question is, can I derive this structure and the exponentiation I presented before without detailed diagrammatics? And relatedly, can I resum the lambda n series? And the common answer, and already, I mean, this is already foretold by the example of, I started with production of multi-particle, is that yes, you can do it, and the trick is, I mean, it's not the trick, it's just the fact that when n is large, if you want to organize your perturbation theory suitably, you have to expand around a different trajectory, okay? So you can organize this computation simply that when n is large, the leading trajectory is not the vacuum. You essentially, you have a large charge that creates a large number of quanta, and then the leading solution dominates the path integral is not the vacuum, but it's a non-trivial configuration. The question is to find this configuration. So let me get to a little bit of technicality. So we want to compute in this theory, and in what I'm saying here, I will be a little bit, I mean, you should think of this as the bare coupling. At the end, the renormalization goes orthogonally to the issue of the semiclassical expansion, okay? You simply have to separate the divergent part when you, I mean, the divergent part from the rest, but the structure of the expansion in n and lambda is exactly the same. So I will avoid talking about bare normalized in what follows. So this is our action, okay? And let me normalize it in the form that is most suitable for doing semiclassical computation, namely in such a way that the coupling comes up front, and my action does not depend on the coupling. Then I want to compute correlators of phi to the n, and the idea is that this phi to the n that I insert when I compute my path integral will force the leading trajectory away from the trivial one. So what I want to do, I want to bring this up in the exponent where we play the role of a source, generating a different solution. So what I want to do, I write it, well, of course, I rescale it, okay? And then I write it as the exponential of something, okay, of the log of phi. And now you see I'm already writing it as, this is going to be e to the n log phi. And again, I can multiply and divide by lambda so that I can write it in terms of 1 over lambda times n lambda. So with this little jujitsu, now I have my correlator written as 1 over lambda to the n. Remember, this 1 over lambda to the n comes because I have rescaled my field, and then there is, again, the path integral, which is my action and my inserted operators, okay? They've been inserted at position xi and xf. This is what I had here, okay? And of course, divided by the vacuum to vacuum amplitude. Okay, so, okay, notice that this path integral looks like an expression that I can compute where I am invited to do a semiclassical computation in the limit where lambda can be treated as a small quantity, regardless of the value of lambda n. In fact, treating lambda n as a fixed quantity. Fixed, but in principle small or large, okay? The idea is that my lambda will be the parameter, the loop expansion parameter, and lambda n is sort of a control parameter. At the end of the day, we will have another also interpretation of what lambda n is in terms of the solution. Just something, notice that this expression, okay, here, this correlator in free field theory is simply given by n factorial times the 2-point function to the nth power. Okay, so in free field theory, remember, this is an n factorial. Just n factorial times f minus xi to the 2n. Now, the point is that now this this integral in the numerator, okay, now we'll have a non-trivial solution, okay, because this phi and phi bar play the role of sources, and you have a solution where phi is different than 0, okay. And there's going to be a saddle point, and which we like to find. Or if you want, at this stage, it's an assumption, okay, but there is a saddle point. Okay, there's a saddle point of this action here, and the saddle point, okay, 1 over lambda is up front. The saddle point will be just a function of this parameter, this control parameter lambda n, and the 2 initial coordinates, xf and xi. Okay, so the saddle point does not depend on the coupling, just depends on this combination lambda n and on the coordinates. Now, the fact that phi is non-trivial around this trajectory means that our solution, given that there exists a U1 symmetry, has a 0 mode, okay? Our solution breaks the U1, okay? Our insertion is U1 invariant, but the solution around which we expand is as a non-trivial phi. So in fact, it's a family of solutions that we have, which is described by a rephasing of the solution itself. It's just a one parameter family. So the existence of this global 0 mode tells you that when you compute the integral, okay, so what you will get that the integral above divided by the suitable normalization is going to take the form of a saddle point approximation. However, the existence of a 0 mode in the upper integral and the absence of the 0 mode here, there's the usual factor of normalization of the 0 mode, which in this case is the usual 1 over square root of the coupling. Okay, so to do things a little bit more accurately, what you get is that you get a semiclassical expression for your 2-point function, and the prefactor has this half integer power of the coupling. Now, remember I said that this expression here in the free field theory case should be n factorial times a simple function of x of the coordinates. So it makes sense to factor out this n factorial, okay? So I multiply and divide here by n factorial. And after I have that net, here I get an n factorial times this power. And now this 1/2 here is precisely what it ensures, thanks to the Stirling expansion of n factorial, that this object can be brought up in the exponent. So that at the end of the day, you have an n factorial, but then you have a series here, which has precisely this form. Okay. So in particular, the anomalous dimension, which is coming from which is associated with the position dependence of this exponent, if you want the derivative of this exponent, okay, it precisely has the form that I mentioned in the beginning, okay, that it is a series in, I mean, there's a polynomial in n lambda plus lambda times another polynomial and so on and so forth. So that all those higher powers of n that I had in my diagrammatic computation actually do not contribute to the anomalous dimension. If you want, this shows the exponentiation I was telling you before. And it's essential for this computation precisely to do this counting of the zero modes correctly. So at the end of the day, I get this. And once I factor out the 3-level result, okay, then factorial, I get which is in the overall normalization, I get precisely a structure for the anomalous dimension. That is what I was saying. So this proves exponentiation to all orders. And what we get is a semiclassical expansion that is valid for any fixed lambda n, as long as lambda is much less than 1. And in particular, notice in this computation, my computation would also work in the limit where n lambda is much less than 1. Okay, as long as lambda is small, I can also, there's also an overlap of my computation with the regime where n lambda is small, where the diagrammatic approach should apply. So my semiclassical computation has also an overlap with the semiclassical method. So there's a way, for instance, to check my results against loop computations, and which we'll do in a moment. So now the main problem, like in the case of particle production, is finding the solution, okay? And the stationarity condition takes this form, okay? Now, of course, I'm looking for, first of all, I'm looking at Euclidean action, and my phi and phi bar, now I'm looking at a semiclassical, I'm looking at the saddle point. I'm allowing phi and phi bar to be not complex conjugate to one another. If you want, I'm going into complex field variables, okay? And so these in general are not complex conjugate to one another in the saddle. And now if I can find a solution to these equations, and then I can perform perturbation theory if I can find the solution to this equation, then I can work systematically. Now, finding a solution to this equation is not trivial. I can certainly look for a solution, and this is very similar to the problem in the case of multi-particle production. I can certainly find solutions for small lambda n. Note that the small lambda n, when lambda is small, doesn't mean that also includes the region of large n. Okay, so it's still interesting. Okay, I'm still considering a situation where I'm including effects with a high number of legs. Okay, so but what we would like to get to is to compute at finite lambda n. Okay, and that is not easy here. Okay, now the basic difficulty is that in order to do a computation, you need to regulate. So as long as you look at this equation here, you can guess the solution. You can get a simple scaling solution. Why? Because this theory is because the theory we start with is classically conformal invariant. So we will have scaling solutions, and you can easily get a quick guess of what the solution will look like. However, in order to do a consistent computation, you have to regulate, going 4 minus epsilon, and there phi to the 4th is no longer scale invariant. So that means that you will not at all dream, you cannot dream of getting a scaling solution. You get a solution whose radial dependence is not simply the power of the radius of the distance between 2 points.
Will you show us the scaling solution? Because that would seem interesting.
The scaling solution, I will show it yeah, the scaling solution, I will find it in a moment by changing slightly the perspective. So the scaling, I mean, the solution here, the classical solution is, I mean, at the leading order is simply 1 over x squared. And then you can find powers of lambda n. And the scaling solution, I will get it in a moment by mapping to the cylinder. I don't know whether, if you wait 5 minutes, perhaps I will answer your question.
Okay. Patient enough.
Okay, so where was I? Okay, so the radial dependence is non-trivial. So the way out, okay, is to focus further the computation and zoom on the fixed point, okay, the Wilson-Fisher fixed point in 4 minus epsilon, okay, where, okay, I mean, as you know, there's a beta function. This is the beta function of the system. It has a fixed point at a certain finite value of lambda star, given at the lowest order by this, okay? And I can, in order to improve my calculational ability, I guess, I mean, going to the fixed point will allow me to have more control on the form of the solution, okay? Now, when I am at the fixed point, I can map, at precisely the fixed point, I can map my correlator on the plane to the cylinder, to the computation on the cylinder. Okay, and here, okay, this is just a brief review of the mapping from the plane to the cylinder. Okay, so I have an insertion of an operator at the origin, an operator far away. The mapping works like this. You have the coordinate r, which is mapped into the Euclidean time log of r, and the origin is mapped to the past, to the infinite past, and the point at infinity is mapped to the far future. And now the 2-point function, okay, and in particular the dimension, is now corresponding to the I mean, dilatations in the plane, which is precisely what would correspond to my, associated with my the scaling, okay, in the radius, gets mapped into time translation on the cylinder, okay. And here comes in a sense the trick that helps, because now on the cylinder what was before dilation now is becoming time translation, okay? And now I can imagine going off criticality for the theory on the cylinder, okay? The theory of the cylinder, even off criticality, has time translation invariance, okay? So it has an analog of the scaling symmetry that was before, but is not exactly the same, because now the theory of criticality on the cylinder is not equivalent to the theory of criticality on the plane. It's only at the critical point that they agree. But but on the cylinder, I still have a symmetry away from criticality, which is time translation invariance. And now, now it's easy to guess what the solution will be, okay? In the limit of a very large time separation, I can guess that my solution will be stationary, okay? And a simple consistent ansatz, okay, in this domain is a solution of this form, okay, which is just in Euclidean time, is just a field that rotates, okay, with a constant angular velocity in this potential, okay. So this is my scaling solution. So this is with this little trick of going off to the cylinder and considering the theory deformed in a different way, I'll now have the possibility to get a simple ansatz, consistent ansatz for a solution of this type. Okay, so this is the analog. So rather than getting a scaling in the radius on the plane, I get a simple time dependence on the cylinder. I don't know add if this partially addresses your question.
I'm actually still confused. Since phi bar isn't the complex conjugate of phi, you need to give a formula for both phi and phi bar.
Yes, this is precisely phi bar is it's the opposite charge, right? They go opposite ways. Phi times phi bar is going to be constant, and this, right? They are one exponentially grows and the other goes down.
I'm confused whether this solves the equation or not, since there's a phi squared phi bar term in the equation, but there's also a curvature times phi term in the equation. So maybe
the terms curvature phi. Yeah, this is what I have in the thing. If you, I don't know whether this, but maybe I show you the next transparency.
Okay.
Okay. Okay. So what does this solution correspond to? It corresponds to the Euclidean version of a homogeneous superfluid with chemical potential mu. Okay. This is if you take it's the Euclidean continuation of such. If you take the theory, the U1 model, a system at finite density with chemical potential mu can correspond precisely to a configuration where the field rotates, okay? And this rotation corresponds to the existence of a charge density, and the phase, the angular velocity is just conjugate to the charge, it's just the chemical potential. So now there's the question. What I would like to compute is the anomalous dimension, or the dimension of phi to the n, defined as the lowest dimension primary of charge n. Certainly in perturbation theory, this is what this guy is, and I take perhaps the liberty of saying that I call phi n whatever it is in the domain of large n. Okay. For small n, I can certainly do perturbation theory and I can identify phi n. At large n, whatever it is, what I want to zoom on is the guy continuously related to phi n when n becomes large. Okay, so the idea here is to try to project my path integral at initial and final states on the subspace of charge n. Okay, and then if I take a large separation between initial and finite time, my path integral will be dominated by the lowest dimension operator, and it will give me automatically by this equation its dimension, and therefore the anomalous dimension. So again, what I want to do is to do a further change of perspective. So rather than inserting this log of phi, I just go to polar coordinates for my field phi, and I insert at initial and finite time essentially the wave function, or the wave functional that projects on a state of charge n. Okay, this is the analog of e to the m phi, the wave function for angular momentum m. Okay, so I write my path integral. Okay, and the action consists of my original action. Okay, and at initial and finite time, wave functionals that project on the state of charge n. And of course, on the cylinder, I have this additional term, okay, which is just giving me a conformal mass term on the sphere. Now I can, of course, this fixes. I should also fix the initial condition for rho. It's up to me to choose the most convenient one, because eventually, whatever I do, for very large time separation, I will unavoidably project on the state of lowest dimensionality, and I can choose rho, the initial rho, such that this solution is the most convenient one. Okay, and this can be done, okay? And essentially, what I choose rho such that it is precisely the value satisfied by, suggested by the equations of motion, implied by the equations of motion. Let me be clear. Let me start with this action, okay? And now chi is the phase of the field phi, and now I want to find stationary points of this action. It will consist of two, the equations of motion will consist of two parts. There's going to be a bulk equation and a boundary equation. The boundary equation is what fixes the chemical potential as a function of the charge, and then there's the bulk equation of motion, okay? In terms of the, so these equations are equations for mu and for rho, okay? So mu is fixed by the charge and the coupling, and that fixes rho as well, okay? And in particular, you put these two together, you get a cubic equation for the chemical potential, okay, which is the Press-Cardano equation, and again, and mu is and rho is fixed by this equation. So if I had chosen if I choose boundary conditions such that rho is precisely given by that, then this is a self-consistent solution. If I hadn't chosen rho that way, then the solution would have a temporary transient. It would not be scaling immediately. It would have a temporary transient where rho goes from whatever initial value I gave to this final one, and then there would be some. But this transient would be localized at initial and final time, okay? And essentially the speed of approach is given by the mass of rho around the solution, okay? If you do small perturbation. And now I solve this equation and I can plug back into the action, and now I can perform a systematic loop expansion. And what I get is that the anomalous dimension takes this form, okay? It's a semi-classical expansion, powers, I mean, it's just the ordinary. I mean, I had my action, okay? My action was here, okay, where was it? Okay, it's this. Of course, I can rescale lambda in front, and then I get that it gets expanded this way. This is gonna be my 3-level contribution on the cylinder, 1 loop contribution on the cylinder, 2 loop contribution on the cylinder. And there is this control parameter lambda n, which is just what gives me the action. And now I can take, now I can start taking various limits and compare, for instance, to known results. In particular, the first thing I want to do is to consider the limit where I'm dominated by the 3-level term. That can be viewed as the limit where lambda star goes to 0, okay? Where lambda star, which is proportional to epsilon, the deficit of 4 minus epsilon, lambda star is of order epsilon. I can take, imagine taking in the limit where lambda star or epsilon go to 0 with lambda star n fixed, okay? So this theory is indeed classical, and the reason why there is something interesting is because I compensate its coupling by taking n large enough so that lambda star n is finite, okay? So this is in a sense is a classical conformal theory, okay? In this limit, I select a classical conformal theory. And now my anomalous dimension, I mean, in this way of computing, and my anomalous dimension, therefore now manifestly in this limit, all the terms apart from the first drop out. And so I get that my leading result is given by this expression. And this is simply given by my action, by the action computed on this solution. And remember, I had a cubic equation, okay? So this is why I will get cubic roots, okay? And this is a closed form expression for my anomalous dimension, okay? In the limit where lambda goes to 0 with lambda n fixed. And this is supposed to resum the leading powers in the anomalous dimension, the leading powers of n for all loops. I mean, if I take all loops, at every loop, I take the highest power of n, and I sum all these terms, this should resum to this result here, okay? Notice that this expression, it has square roots and stuff like that, but for positive lambda n it has a finite radius of convergence in lambda n going to 0, okay? So I mean, I can extend it analytically to all lambda n. It's very similar to what you have when you do RG, okay? It's not an asymptotic series in lambda n. This is just, it has a finite range of convergence. And the point where you have the singularity, if you want, corresponds to the values of this parameter, of the parameter x, for which the mode associated with this radial degree of freedom becomes tachyonic. Okay. So if I expand this expression, so this expression contains all leading powers of n. If I expand it at small lambda n, I get this expression, which invites comparison with the first the computation of the diagrams. And you see that the leading terms, this and this, at 1 and 2 loops do indeed coincide, okay? And so this is indication that what we're doing makes sense. They agree. In fact, this invites us to check the subleading terms, okay? And now to compute the subleading terms, you really have to do a one loop computation on the cylinder. And in order to do that, the fixed point condition is essential, okay? And okay, now the diagrammatic computation gives this result for anomalous dimension at this order, okay, including the subleading terms. And now in the computation, I mean, this is the diagrammatic computation, and the semiclassical computation. Now the subleading term should come from the Casimir energy on the cylinder. This you can compute, okay, just standard computation. The Casimir energy converges for sufficiently low dimension. And now, well, okay, you get a few steps, and then you go through, and it matches perfectly. Okay, so this also works. In fact, we can use our computation to do a further check. In fact, what I showed so far is only, I mean, these are homemade computation at 2 loops, but people have actually computed the anomalous dimension for all n up to 3 loops. And they've also computed the anomalous dimension for phi squared, phi cubed, and phi to the 4th up to 5 loops, okay? And now I can first, certainly I can check, I can totally match the 3 loop computation, and it works. And now at 4 loops, I have 5 parameters to describe the 5 loop. See, the loop expansion at small lambda n, at small n in the domain where Feynman diagrams approach works, order by order in the expansion in epsilon, you get, okay, at each order epsilon to the L, you get a polynomial of order L for the anomalous dimension, okay? So the higher loop you go, the more powers of n, and the more, if you want, free parameters you get. Each coefficient of n is a free parameter. Now, people who do computation of loops have done this I loop computation only for specific phi squared, phi cubed, phi to the 4th. However, using the form of the result as a function of n that you expect from the simple combinatorics by inspection, and our explicit result, which basically gets to all order the leading and subleading terms. Namely, we get at all order in epsilon the leading and subleading powers in this polynomial, allow us to boost the present computations, which were only valid up to 3 loops for arbitrary n, to 5 loops for arbitrary n. Okay, and again, at order 3 loops, our results perfectly matches the general computation, and at order 4 loops, it consistently matches, and it makes an additional prediction. And at order 5 loops, it allows to compute completely the terms. Basically, if you want at 5 loops, people have computed for the anomalous dimension for 4 operators, okay? But there are 6 coefficients. The other 2 are, so now there are 4. We need 6 conditions. 4 are given by the finite loop computations, and the other 2 are given by our computation of the leading and subleading. So using that, we were able to boost the computation up to 5 loops. Remaining in the domain, just for simplicity, at the leading order, one can now consider what happens in the limit of very large charge. Very large charge here corresponds to the regime where lambda times n divided by pi square is much, much bigger than 1. Okay? In this regime, the form of anomalous dimension is this. Okay? You have these powers, these apparently weird powers of lambda times n. Okay? 4/3, 2/3, 0, minus 2/3. And what is the interpretation of this result? Well, the interpretation of this result is the following. Okay, this is the regime where you have a very, very large charge density on the sphere. Okay, and so the sphere has a certain radius, but the charge density, okay, introduces a new scale which is much, much shorter than the radius. Okay, so there's a new length scale. You can view it as a spontaneous breaking of scale invariance because of the presence of this non-trivial, you are in non-trivial configuration, okay? And so there's a new scale associated to the charge density, okay? And this new scale is what controls now the mass of the radial excitation. The radial excitation is as a gap, which is much, much bigger than the inverse radius of the sphere. So what you can do, therefore, is you can integrate it to describe the physics at around the radius scale. You can integrate it out, and what you're left with is an effective theory for just the phase excitation, which is the phonon mode of the superfluid. Okay. In other words, this system has 2 degrees of freedom, the radial mode and the phase around the solution, and in the domain of large charge, the radial mode is heavy. You can integrate it out. And when you're left, it's a pure conformal superfluid in 4 dimension, because we're taking the leading epsilon going to 0 limit, a conformal theory of one mode, chi, with a shift symmetry, okay? And the most general form is given by this, okay? And now the chi is fixed by the charge density, and now you get precisely the scalings. These different powers of lambda n simply corresponds to the derivative expansion. So this expansion here just corresponds to the derivative expansion in the effective theory for this conformal superfluid. And this is the 4-dimensional analog of the known large charge behavior that is known to be a universal feature of conformal field theories, which was studied mostly in 3 dimensions. Okay? Both using semiclassical methods here, but also using the bootstrap. Okay, so this is just another way of deriving known results. Again, if you consider the quantum corrections at finite epsilon, they will give you some logarithmic dependence, okay, on epsilon. And this is precisely compatible with the scaling. Okay, this is, for example, looking at large epsilon n. This I'm looking at the case of large epsilon n. So the case of large charge at arbitrary epsilon. And so you can reduce the form of the anomalous dimension as a function of epsilon for large epsilon n. And given that we have the leading and subleading term, our computation encourages a perhaps naive, but still worth doing, comparison with Monte Carlo computations in 3 dimensions. Okay? In other words, we know the epsilon expansion roughly works, okay? That if you go up to high order in epsilon, then you extrapolate epsilon to 1, you get closer and closer to the proper results of the corresponding critical three-dimensional theory. And here we start seeing, at least for the first coefficient for the leading dependence in N, you get that the Monte Carlo gives this result for the coefficient. At the leading order, we get 0.47, which is not far, but not close. And then if you add the additional correction, you get closer. For the second term, it doesn't work so well. Okay, this is the Monte Carlo result. The leading order in epsilon, it's considerably bigger, and then it bounces back to this. It would be interesting to do the two-loop computation, okay, to see what happens. Okay, but in principle, this is for those who do this epsilon expansion for the community that does this type of computation. This is certainly a type of computation that can be systematized. You can also do, we also thought about, I mean, we also consider the case, a similar case, the case of 5-6 in 3 minus epsilon, okay? This is another, it's a critical point, okay? Now, the peculiarity of this case is, with respect to 5 to the 4th, is that the beta function comes at 2 loops, okay? So when you consider the theory, the computation of anomalous dimension working on the cylinder, what you have is that at least at the 3 level and at the 1 loop, okay, you can consistently work going to epsilon equals 0, because the knowledge that to be at the fixed point only comes, I mean, the beta function, the non-trivial beta function comes at 2 loops, so that at the leading order in epsilon, I mean, you can work at the leading and subleading, you can work, you can really take the limit epsilon going to 0. And this is interesting because that means that our 1 loop computation, okay, now we can really take the epsilon going to 0 limit in this 1 loop computation and compare to, I mean, this 1 loop correction interpolates for at small lambda n, when epsilon goes to 0, at small lambda n with diagrammatic computation, and at large lambda n with the computations done in the universal CFTs, like in the paper of Hellerman and collaborators, and of course the thing matches. In other words, we have a closed expression that interpolates between the universal large charge expansion in CFTs and diagrammatic computations. So let me conclude. The Wilson-Fisher fixed point, I think it provides a simple but rich playground to get structural insight in the large, in the regime with large number of legs in quantum field theory. Now, as I've shown, the loop expansion, at least for the anomalous dimension of phi to the n, or if you want, of the lowest dimension operator with charge n, is non-trivially and systematically encapsulated by a semiclassical superfluid configuration. So the configuration that dominates, in other words, the correlators, the computation of this large and I mean, deep inside this computation with large charge, there is dynamics of a superfluid. Okay, so in particular, I could also consider not just this operator phi n, but the nearby operators. Okay, because I not only have if you want the vacuum, the minimal energy state with charge n, I can also now consider the Fock space of excitations around it. Okay, and these excitations are nothing but the hydrodynamic modes. So there is a correspondence between the spectrum of operators that are around this phi to the n and the hydrodynamic modes. Okay, and also correlators can be studied by extension of the method. Okay, and if I can make just a little comment, there is a sort of toy analogy between this system and systems where lambda n is indeed the Toft parameter. This is not the Toft coupling, but this is somewhat vaguely reminiscent of a situation in the SCFT. Okay, there lambda n is the Toft coupling, and lambda n controls, if you want, the UV completion of the universal supergravity degrees of freedom. Here, lambda n, when lambda n is large, controls the UV completion of our simple superfluid phonon mode, okay? It's the mass of the radial mode, okay? So there is this sort of analogy, although there's no holography here. This is just, and again, there is also so in other words, there is the analog, if you want, of the supergravity description limit is our simple superfluid.
So actually, I'm glad you said that, because I wanted to connect this to an example where, in fact, it is holographic, and it is, I think, like what you're talking about. So there are examples with small MC but large charge in holography where you do get
I see.
a Twift expansion. So I've been very, very curious since we stumbled on that some years ago with Polchinski, where, for people who know what these are, you know, it's a 1-5 system where you work with the 5-brane theory and think of the 1 branes as excitation of charges in that 5-brane theory. The 5-brane theory doesn't have to have a large NC, and yet the whole thing has a good dual geometric interpretation. I always thought of that as a sort of peculiar thing to, you know, there's a matrix, you know, understanding of the 1 branes by themselves, and I thought that accounted for there being this this Twift expansion and this dual geometry. But now you guys are coming along and saying how much more general that is, and so yeah, I'm very curious as to whether indeed this there is, you know, under what, in what situations is there in fact such a Twift expansion that describes a dual geometry. Maybe must be related. If so, it must be related to your hydrodynamic degrees of freedom. But yeah, just
I wouldn't be able to. Yeah, I don't know. Actually, it would be interesting to know. By the way, in a similar context, but in the context, but with supersymmetry, in the work by Komargodski and collaborators, there the lambda n is associated this topological expansion. I mean, this lambda n becomes really a Twift coupling of some random matrix model.
Right. We actually had that talk.
And Zohar was interesting to know whether our situation had an analog matrix model. I don't know.
So I had another question more directly related to your talk, which is you did Wilson-Fisher with, you know, small epsilon, then you tried to think about maybe being able to get to epsilon equals 1. What about theories that are weakly coupled fixed points, say like the ones that Appelquist studied in 3 dimensions, involving gauge fields and large NF matter? Could you study those similarly, and then it would be more?
Yeah, you could also use 1/n instead of epsilon.
Yeah, exactly.
Right. Exactly. Yeah, this was done. Actually, I think this was done already by Orlando, Reffert, I think also Luisa Barreto. Yeah.
Yeah. Just for the obvious reason that is.
Yeah, they did it. Yeah, this is doable. Instead of epsilon, you can use. So essentially, now you're going to have n legs divided by number of color, yes, or number of flavors.
Number of flavors, right. So it's in a physical dimension all the time. So that's, yeah.
Right.
Thanks.
And of course, it would be nice to get back to the question about particle production, even if only at threshold. I don't know if Lance maybe he's not happy because, but at least cleaning up the situation there, it would be worth having it. But
you do what you can do.
You
do what you can do.
You do what you can do. It's dirty.
It looks no, it's pretty interesting for these other systems. And
for that system, I think it's clean and it's not uninteresting. Yeah, I mean, of course we care about the standard model and particle physics, but there are other systems.
So this gauge theory one would be, if I understood it right, like the Banks-Zaks fixed point.
Yeah, exactly.
NC and NF, so the first coefficient of the beta function is very small, and then you tune that against 2 loop, and then you could look at operators with, for example, very large numbers of field strengths, Is that
But I think you can also look at directly in 3-dimensional large N fixed points, right?
Right. So it's
You
analogous.
can also look at you go directly to 3-dimension. You have large N theories,
just
and
saying
then
you could do it in
large
4
charge
dimensions,
in large N.
with Banks-Zaks, but okay.
You can also do it by Zaks, yes,
There's
sure.
a 3-dimension one also.
But you can go directly to 3-dimensional theories with large N. You could approach, for instance, O4, starting from ON and then going right.
How hard is it to get the next term in your expansion? In other words, suppose you want to predict the terms that are down by 2 powers of n. It's like a 2-loop fluctuation around the classical solution or something like that.
Right.
That's probably pretty tricky.
There you is like doing next to next.
Does that look very hard?
Actually, we thought of giving it to a master student.
Oh, not so
and
hard.
Then we got stuck.
Unless it's a good master student.
we got stuck, and then the master student moved to computing correlators and with us. But hopefully, yeah, we were a bit slowed down. Yeah, I think it's doable. It's just that at least myself, I'm not technically too suited, but it's doable. Yes, it's definitely doable because you're doing 2-loop computations on the sphere. But by the way, are you familiar of people who know how to do these things? Who have all tricks how to manipulate these sums?
Well, certain types of sums I'm very familiar with. I mean, you got these zeta values there, and those are various types of the first example of nested sums. And if you're getting, but they're not nested if they're 1-dimensional sums. But at 2 loops, you might get nested sums. And then there's a huge amount of, if it's the right kind of sum, a lot of technology built up that is related to.
Well, we will ask you.
You can ask me
to find
if
it.
you need a sum done or something like that. I was going to ask you actually what form the sums emerge. They must be some kind of a determinant of the fluctuation.
I must admit that I haven't looked at this. It was actually maybe some of my collaborators, if they are connected, they can say what the sum is. I haven't been looking at this in this recent month. I really cannot answer that. It's better if I don't. Okay. It's better if I don't.
Yeah, I wish I knew better what the lore is about how fast things fall off with epsilon as you move away from threshold. I know there was some work in the 90s looking at that. I just don't.
Yeah, but they never got to the point where which is the point where this f, if you want to get to the f, I mean, the point where f may start flipping sign is precisely beyond where you can compute your solution.
So how far does unitarity get you in this? In trying to, how far does unitarity?
Unitarity, no, this thing cannot grow. Okay, what may happen is that it gets saturated. Okay, this could happen in principle.
But doesn't unitarity often involve going into something like partial waves, which requires you to smear things around in different directions? Maybe if you're exactly at threshold, I guess.
Yeah, not too away from threshold.
Maybe you
could have a small region close to threshold where you saturate unitarity. I don't know. Could be. It's logically possible, but.
I mean, it almost did sound suspicious, but it is a fascinating idea that the Higgs fails to be a good quasi-particle. So it seems like it's worth, totally excluding the possibility.
Yeah, that's essentially my take. To avoid, I mean, this is the standard model, so we should know. We should have clear ideas of what happens in a theory like that. Okay, so we should avoid having confusing statements. We are building these machines, right? I mean, even if it's a tiny, again, Lance say, oh, it's just a threshold. Yeah, sure, but come on, it's a 100-kilometer tunnel. We know what we are doing. We've computed all that we could compute, and we know what it is.
All I'm saying is to get something big, you have to get the amplitude big, but you also have to get the phase space.
Phase space, oh, we certainly know that, yes. Certainly know that, yes.
So is there any chance of some sort of experimental probe of this in a more condensed matter setting?
I mean, considering this, I mean, computing.
Something about the large charge sector, and then, you know, say in some case where either you have a formula to compare it to experiment or you don't and you want to know, you know, so you use the experiment to determine it. I mean, yeah, I'm just wondering if there's.
Yeah, I mean, the closest we get to experiment here is checking with Monte Carlo. And
no, I understand, but
yeah. But it's also with turbulence, right? The things that you know best are done with numerics rather than with experiments.
Well, but you did mention, you know, critical points in real materials. So whatever. It's just a question.
You can get superfluids that you can rotate them. Does that give you a large charge of angular momentum? Can you do anything there? I don't know.
No, you can have. I mean, why angular momentum? I mean, you can have you have critical systems in 3 dimensions that precisely this U1. Like there are quantum critical points with U1 symmetry, and I mean, why? And at some of these points they have exactly conformal symmetry. You can see them in the book by Sachdev. Now, I don't know how experimentally how to create an object with large charge in these systems.
I'm just saying, in superfluids and superconductors, I think it's easy to do. So maybe.
I mean, having large charge objects. Oh,
well,
you mean
by a charge? I mean angular momentum. Is that?
Well, this is a different charge, right? Now it's a space-time charge, right? So
yeah. Is there any analog of this for that?
Well, we studied. I mean, we studied in the case of 3-dimensional U1 models. We were able to study operators with large charge and large angular momentum. Both large, however, not.
Okay.
There's always large charge.
Okay.
So you're saying there's no experimental setup where you can get some large internal global charge excited. I mean.
Well, I mean,
I don't know.
Oh, that's a question, I guess. I mean, related to my earlier comment about there being at least some examples where large charge does translate also into a dual geometry, there's this very, very, very aspirational idea of quantum gravity in the lab, and you know, this seems to be somewhat related to it. If all of those things were to work out.
Yeah, this I wouldn't be able to comment on.
Well, I mean, the first step would be getting some experimental setup, and then it would have to also be true that it was really large radius for this aspirational thing. But anyway, even any normal experiment would be great.
I must admit that when we first did the thing, I thought about yeah, I mean, what happens. So when you have this, I think one way. So essentially, complicated. Yeah, I mean, no, you would have to work on the cylinder. But no, but then it's 2 + 1. Yeah, I wouldn't. I don't know. I don't know how to set up the experiment. I don't know how to set up the experiment.
So I think Mehrdad Mehrdad, did you have a question earlier? I thought I saw you try to ask something, but maybe not.
Yes, but it was very technical, and I think I got the answer eventually.
What was the question?
Well, at some point you were writing the wave functions to project into particular charge. And
Right.
you had these chiitons and they were under the integral over time.
Yeah, because I'm only projecting the zero mode of the field on the sphere. Because I'm fixing the global charge. I'm fixing the total charge, and the total charge is associated to the zero mode of the phase, right?
Yeah, but shouldn't it be just at the two ends of the path
It is at the two ends. It is at the two ends.
I think in your expression, they were inside the tau integral.
Oh, what an idiot. You're right. You're right, yes. They are at the end points, sorry. In fact, I was talking about the boundary equations of motion in the bulk. These are at the boundary. Sorry, there's a typo in this formula. The integration over time is only for the first three terms. The last two terms, proportion to chi, are only at the boundary. It's good that you asked.
Thanks.
Sorry. Yeah.
Well, are there any other questions?
Hi, I have a simple question, Riccardo. So what about a non-abelian Goebbels symmetry?
Well, yeah, then you can do similar things. It's only more complicated because there you have, yeah, you could do it in principle as well. I mean, you just have something more complicated, but you can do it.
Okay.
There you have these more exotic superfluids where you also have gap modes. Okay, if you have non-abelian charges, now your Hamiltonian, the effective in the time translation operator on your solution is going to be a linear combination of the original Hamiltonian and the charge, but the charge is non-abelian, and then this does not commute with other charges, and therefore the Goldstones, or if you want the soft modes, are not soft. They have a gap completely fixed by the chemical potential. You have this famous example of gap Goldstones. So, but in weakly couple, so now in the effective theory description of this gap Goldstones in the universal case, like in universal CFTs where you don't know the microscopic description, I mean, you just say a universal CFT with an abelian, non-abelian O4. What is the general scaling? I mean, what is the general description of a large charge state? Okay, then the problem there is that these gapped states have a gap which is of the order of the same order as the gap of other non-universal modes. So you really have to zoom. You have to write a specific effective field theory for slow-moving gap Goldstones. We wrote a paper last week on that. But if you have the microscopic description, like in this weakly couple case, then I think it's just a generalization of what I'm doing here.
Okay, so is the essential means so this U1 because they have superfluid description? Why the U1 is very essential here? The U1 global symmetry.
Oh, because I can associate. I mean, I can really fix. I can associate this large charge so I can project on the. So I don't know how to say it. You're asking why is it? See, the very fact that on the cylinder I have both charge rotations and time translations, okay, allows me to have the stationary solutions where the solution is time dependent, but I still have time translation invariance because there's a linear combination of time translation and charge rotation that is unbroken.
Okay. Okay.
And, so it's essential to have this charge.
Which means you have Goldstone boson associated with the charge. That's why you can do it. Okay, okay, thank you. Yeah.
I mean, that's simpler to answer. I mean, I have a simpler solution.
Okay, thank you.
Are there any other questions? Well, if not, let's thank Riccardo by applauding.
Thank you.
Thanks, Ricardo.
Thank
Yeah,
you.
thank you so much for coming at this ridiculous hour. That talk was wonderful. Thank you so much.
Yeah, thanks, Ricardo.
Thank you. Thank you.
Yeah, it turned midnight and you didn't turn into a pumpkin. It was great.
Well, I was already a pumpkin. I was already a pumpkin before midnight.
Yeah, I